All right, no comments on the last lesson's homework assignment this time. We're just going to go right into lesson 13-7. And I got a blank copy in front of me here. We're going to read through the problem, talk about it a little bit, and then I'll move that aside to reveal the work of the finished copy. So let's read the problem. Campbell's is producing 2 different sized cans of tomato soup. And here are the costs associated with the production of the store-sized small can of soup, the kind that you would, get in any store. So the cost for the soup itself, 25 cents. The cost for the metal to make the can, 13 cents. Cost for the paper label to go around the can, 2 cents. And the cost for the glue to glue the label together, right? Because they wrap that label around and then they got to glue it together. Note that the label is glued by wrapping the label around the can and then laying a thin strip of glue along one edge of the label and pressing the edges of the label together. It's sort of like, this piece of paper, which I've formed in and out of cylinders. You've seen me handle this piece of paper several times already. This is a sticky note, right? And there's sticky stuff just laid right along this edge of the sticky note. And if I formed this into a cylinder and then just stuck that edge to itself there, right, then this thing would be stuck into a cylinder shape if that stickiness were still holding, right? So the glue is just laid along one edge of the paper label, okay? So now, Campbell's is going to make an industrial-sized can, a really large one, for huge kitchens like cafeterias, like maybe our school cafeteria. They make a super large-sized can of soup. And all the dimensions, all of them, the height, the width, the length of the can, they're all 5 times that of the small can, which is sold in stores, okay? So what are the costs associated with the production of this industrial-sized can of soup? Now, if you're on your toes at all, you're probably thinking, well, to just multiply all of these costs by 5, it would be too easy. That wouldn't be worth a whole lesson. There must be a different way to come up with the answers to these questions. And you'd be right. And also, if you've been really soaking up what we've been saying about areas and volumes of things all along the way since, I would say, the end of Unit 12, you might have some sense as to what we would need to do to these costs for the small can to arrive at the costs of the new can. But again, before I show you the results, let's just think about how we measure soup. Okay? Would it make sense to say I have 3 centimeters of soup, like a line of soup, a thin line of soup? Would it make sense to say I have 3 square centimeters of soup, like a completely flat, square of soup? Or would it make sense to say I have 3 cubic centimeters of soup? Certainly cubic centimeters makes a lot more sense, doesn't it? Now, soup doesn't come in the shape of cubes, of course, right? But still, soup is a volume of stuff. You measure soup by its volume, okay? How about the metal used to make the can? Now, this could be a little tricky, okay? Would it make sense to say I have 3 inches of metal, a strip of metal? Or would it make more sense to say I have 3 square centimeters of metal to make the can? Or 3 cubic centimeters of metal to make the can? Now, this one could be a little bit tricky, okay? But really the correct answer here in terms of the context of this problem is that the metal of the can, the measure of the metal of the can, it makes most sense to talk about it in terms of square centimeters. And while, yes, the can has kind of a thickness to it, the metal has a thickness to it. It may be very, very thin metal, But still, as thin as the metal might be, it is a thickness, and we can talk about the volume of metal. That thickness of the metal is not really going to change from the small can to the big can. They're not going to use a thicker metal to make the can. They're going to use the same thin metal sheet, but it's just covering a larger can. It's wrapping around a larger volume of soup. Okay, so the metal really should be thought of as an area type of thing. The paper label, that definitely is an area thing. Again, the label going around the can, we've talked about that multiple times. It unwraps into a nice flat rectangle. And then the glue, okay, again, think in the context of this problem, how we described how the glue is being used. Would we say we're using 3 centimeters of glue, 3 square centimeters of glue, or 3 cubic centimeters of glue? Well, we're laying a thin strip of glue. We're drawing, just a line of glue down the label. We're not gluing the entire area of the label, right? We're not covering this whole area with glue. We're just lining one edge with glue. So it makes more sense to say we're using 3 centimeters of glue or 4 centimeters of glue or whatever. So this soup is measured as a volume. The metal and the paper makes sense to talk about their measures as areas, square units, and it makes sense to talk about the glue as a length. Okay? So there's your clues to how to get the correct answers to these questions here. So now let's reveal the work. Okay? Here are the costs that I've written down associated with the small can, the can you buy in the store, 25 cents for the soup itself. But soup is measured in volume, right? So we're not going to multiply the cost just by 5. We're going to multiply the cost by 5 cubed. All right? I think this is the first time we've seen this sort of thing. All right? And 5 cubed is 125, and 125 times 25 cents, well, that comes out to 3,125 cents, or $31.25. Okay? The metal, which is essentially covering the surface area around the soup, right? We're not going to multiply the cost of the metal by 5, but by 5 squared, because we'll be talking about that metal in terms of its square units, square centimeters or square inches or whatever. So we're going to multiply by 5 squared. The paper label, that's also an area type of thing. So we're going to multiply that cost by 5 squared. And then finally the glue, since we're just drawing a line of glue down the edge of the paper, we're just going to multiply the cost of the glue by 5. Okay? So the cost of the glue goes from 1 cent to 5 cents, 5 times as much. Cost of the paper gets multiplied by 25. Cost of the can gets multiplied by 25. Cost of the soup itself gets multiplied by 125. Okay? So on this homework, I've got, I think, at least 2, maybe 3 problems that have to do with 3-dimensional objects. And yet, any 3-dimensional object has a volume, it has a surface area, and then it has individual length measurements in one direction or another. Okay? So if we're growing a 3-dimensional object, by, let's say, 5 times, any cost or any, let's say, time associated with the volume of that original object is going to multiply, is going to get multiplied by that growth factor cubed. If we're talking about not cost, but let's say, time, I could ask this question. I could say, it takes 25 seconds to fill the small can with soup. 25 seconds. So then how long will it take to fill the large can with soup? Okay. Well, filling the can with soup, we're filling the can with a volume of soup. So if it takes 25 seconds to fill the small can, for the large can, it's going to take 25 seconds times 5 cubed. Okay. What if I talked about painting the can, and I said it took 13 seconds to paint the can? That's just how long it takes to paint the outside of the can, 13 seconds. Okay. And then for the large can, it's going to take 13 seconds, not times 5, but times 5 squared, because we have 5 squared times more surface area to paint. Okay. Paper label, well, that's the same kind of question. And then what if we were just painting, I don't know, some length on the can somewhere? Maybe we were just going to paint a small yellow strip around the center of the can, or paint a small strip from the top to the bottom, or something like that. And then if it took us 1 second to paint that strip on the small can, it'll take us 5 seconds to paint that strip on the new can. I think pretty much all the problems that I find natural to come up with for a lesson like this have to do with costs or with times. So that's what you're going to run into. All right? Maybe let's take a look. All right, so I got a small model of an automobile in problem number 1. And I'm talking about the amount of paint to paint the model. Okay. Now, when you're painting a model, okay, what is it about the a model that you're painting? That may sound like an awfully vague question. Okay, but we're painting the outside area of the model, right? We're painting the surface area of the model. I know, don't be confused here. 0.2 fluid ounces, that is actually a volume measurement. We have these funny ways of measuring things in our American system. We don't often say cubic units of things. We use terms like ounces and pints and gallons and quarts and things like that. So that is legitimately a volume measurement, but we're using that volume of paint to paint the surface area of the model. Okay. It says the model weighs 5.5 ounces. Well, what is the weight of something dependent on? Is it dependent on how much surface area there is of that thing, or is it dependent on the volume of stuff? It's dependent on the volume, right? Weight is related to the volume of something. Okay, what's the next problem here? Oh, I got a swimming pool. All right. So this problem is a lot like the soup can problem, okay, in that we're filling the swimming pool with water. We're cleaning the sides of the swimming pool, the surface areas of the swimming pool. And then for a boat to cross the swimming pool, that's just a linear measurement. Okay. And then there's a third problem here, again about soup, which I won't say any more about because it's so much like the example problem. I don't honestly know why I have this problem on this assignment, because it's exactly the same as a problem on the previous assignment you just did. Maybe, I don't know why. I'm not even going to speculate why I had it. You can probably just ignore it, skip it, okay? But then I like this problem a lot. Imagine you have a solid cylinder of clay, and then you cut out a 1/4 section of that solid cylinder of clay. Okay, volume should be pretty straightforward. Find the volume of that cylinder of clay as if it was solid, as if it was a whole entire cylinder, and then just multiply by 1/4. Right? But this total surface area, that's going to be much more interesting. How many surfaces do you have here? Count them up. You have 5 distinct surfaces here. Now, some of the surfaces have, congruent partners, like this rectangle in front and this rectangle around the side. They're the same size, but they are 2 distinct surfaces. Okay. Then you've got this quarter circle on top, and you've got a quarter circle on bottom. So there's 2 more surfaces. And then you've got that lateral surface around the back, right? And that is 1/4 of the lateral surface of the entire cylinder. Okay, so 5 distinct surfaces, although I imagine if you put that quarter circle together with that quarter circle, you could imagine that it's exactly 1/2 of a circle and do one calculation to find the combined area of those 2 quarter circles. Okay, so that should be interesting. And then what do we have on the next page? Oh, another interesting problem. I love this one too. Okay, this is a solid wooden cone, solid, with a 90-degree wedge cut out of the cone and tossed away. So volume again should be fairly straightforward. Volumes are always far simpler than surface areas. Why should this be so straightforward? Well, just find the volume of this cone as if it were solid, as if that section hadn't been thrown away, and then multiply that answer by 3/4, because that's how much of the cone is still there, right? Should be easy. The surface area. Okay. Well, let's start with the base of this cone. If it were a solid cone, it would have a perfectly circular base, right? But in this case, it's not a perfect circle, but it is 3/4 of a circle. So that would be your base area. And then you've got these 2 little triangles on the inside, right? We didn't used to be able to see those triangles until we cut away that section of the cone and threw it away. But now we can reach in and touch those triangles. They're surfaces that we can touch. They need to be counted. So find the area of each one of those triangles. By the way, this says that the radius of this cone is 5 and the height is 12. That height is this height right here. We talked about that before. There are 2 different heights for a cone, right? This is the height of the cone. And then from here to there, that's also a height, but it's called the lateral height of the cone. You're going to need this height of the cone to find the volume, okay? And you're going to need that height also to find the areas of these triangles. But to find the outer surface area of this cone, the lateral surface area, okay? And remember, we talked about that before. That could be unwrapped, and it would look like this. It would actually look like a sector of a circle. Right? We've got a formula for that. Go back and look it up on a previous handout if you need to. There's a formula for the lateral surface area of a cone. You're going to need the lateral height to do it. But again, keep in mind that this is not the full lateral surface area of this cone because part of that cone has been thrown away. So calculate first the full lateral surface area of that cone and then multiply that by what fraction? 3/4. So 3/4 of the lateral surface area, 3/4 of the base circle, and then add in those 2 triangles, and you should be good. Okay? We'll see you next time.